Hey, good people, this is Arthur Morris. Welcome back. In this video, we are going to look at linear systems that have no solutions or infinitely many solutions. Infinitely many solutions. All right, so we've already looked at uh, systems that have exactly one solution. That's where those lines would intersect. Now, if the systems have no solutions and we were to graph that system, then the lines would be parallel to each other and they would never touch or never intersect. Therefore, they wouldn't have any point in common, any ordered pair in common. If the system has infinitely many solutions, that means that the two lines are identical or the equations are the same, maybe just have different coefficients, multiplied coefficients. But if we simplify both equations, they would be exactly the same. So the lines coincide if we were to graph those. So how do we tell that we have no solutions or infinitely many solutions when we're given a system of equations? Well, uh, we'll still go ahead and use either the substitution method or the addition method and solve, and we'll have special solutions that will help us to identify if we have infinitely many solutions or no solutions. So here I have the equations 3x minus 2y equals 7 and 6x minus 4y equals 9. So I'm going to use the elimination method and I'm going to eliminate the x's. So I want to make those x's have exact opposite coefficients. Well, the least common multiple for 3 and 6 is 6. My second equation already has positive 6x, so I need to multiply my first equation by a value that would make that 3x into negative 6x. So let's multiply equation 1 by negative 2. Okay, so now I will rewrite my equations. Equation 1 being multiplied by negative 2 gives us negative 6x plus 4y equals negative 14. Equation 2, leave it like it is. All right, so now look, remember after we make those variables have opposite coefficients, then we add the two equations together. If I add negative 6x plus 6x, that's 0. If I add positive 4y minus 4y, that's 0. So I end up with 0 equals negative 5, which is not a true statement, and my variables are gone. So if you have a situation where both of your variables cancel completely out, then you have a special solution, first of all. And if the statement that is remaining is false, then that means we don't have any solutions for the system. Which also means if I were to graph those two lines, they would be parallel and they would never intersect. So no solution if both of the equations eliminate each other. Both of them, not equations, sorry, both the variables eliminate each other, and the statement that is remaining is not true. Okay, let's look at another example. So in this system, we have 2x minus 7y, or minus y equals 7, 2x minus y equals 7, and 6x minus 3y equals 21. So here I'm going to eliminate the y variable. So I know that my least common multiple for 1 and 3 is 3. However, I need to make one of those positive. Well, since I already have negative 3y in equation 2, then I'm going to make the y in equation 1 into positive 3y by using multiplication. So I know a negative times a negative makes a positive, so I will multiply equation 1 by negative 3. That will give me negative 6x plus 3y equals negative 21. In equation 2, I already had the number that I wanted on y, so I'm going to leave it exactly like it is. All right, so here, negative 6x plus 6x is 0. 3y minus 3y is 0. Negative 21 plus 21 is 0. 0 equals 0. Both of my variables eliminated each other. Uh, the statement that I have remaining is true. 0 does equal 0. So that tells me that I have infinitely many solutions. And again, if I were to graph those two equations, it would be the same line. Alrighty, good people. I hope you found the video to be helpful. I will see you on the next one. Thank you.